So I'm going to just temporarily mute you. You can unmute yourself if you have questions, but that way there's no like feedback or anything like that.
Yes.
Okay, so what does it mean to be one-to-one? So we have this phrase or this term one-to-one. If for A and B in the domain of F, this is the definition, it's a very mathy definition. If A is not equal to B, then F of A is not equal to F of B. What it's essentially saying is if we think of this as ordered pairs, if I have like an ordered pair, 1 or 0, 1, and let's say I have another one that's like -1, 5, it is one-to-one as long as if the X values don't match, the Y values also don't match. It's weird to think about it that way. So we actually usually think of it in terms of what's called the contrapositive. And the contrapositive just means you flip it and then you take the opposite. So we usually think of it that if F of A equals F of B, then A equals B. The contrapositive here is saying that if your Y values are the same, then your X values must also be the same for it to be one-to-one. It basically means that you can't have the same Y values at 2 different X values. So it's sort of like the definition of a function was you can't have the same X value have 2 different Y. One-to-one is the opposite. You can't have the same Y values have 2 different X values. So it's like the opposite or the inverse of the definition of a function. So you can't have the same Y values at different X values. So if you have matching Y values, then they have to be the same X or the same point in order for it to be considered one-to-one. And so generally we talk about functions being one-to-one, which means that they go both ways. So it's a function, so every X only has one Y, and then it's one-to-one, which means every Y has only one X. So essentially what that means is you can't have any repeated values. So you only have, if you were to graph it, every X shows up once, every Y shows up once, you don't have repetition. So I'm going to look at this in terms of a relation, which is just another way of saying we have a set of ordered pairs here. So it's a set because it's in curly braces. And then I've got 4 ordered pairs. So it is one-to-one if it's a function and if it's basically got the one-to-one in the other way. So we have to basically check both. So sometimes it's easier to kind of make a drawing where we think of the input, and you can think of it as a box or a circle, and then you have like the output. And so our input values are the X values. So I'm going to just list all the X values we have here in our ordered pairs. We've got -14, we have -2, we have 7, and -9. And then the output are the Y values. So I'm going to just list all of the Y values we have. So if you plot something here, one-to-one function means every X goes to only one Y. And then you also have to have it go to the opposite direction. Every Y only goes to one X. So I'm going to start drawing arrows here. So based off of the ordered pairs. So our first ordered pair is 14, 1. So I'm going to draw just a line in between those. And I have -2, 3. So I'm going to connect those. We have 7, 4, and then -9, -2. So what because each number on the left only goes to one number on the right, and each number on the right only has one number on the left, this is 1 to 1. So drawing a picture like this kind of helps you figure out or understand what it means, because you can see that each number goes to one other number. That's sort of what it means, 1 to 1. One number to another one number. So it would be not 1 to 1 if you had some numbers having more than one kind of connection here. Now, this concept of 1 to 1 is actually important in databases and computer science, because when you're designing a database and you have certain fields that you might be keeping track of, you have relationships between one table and a number table that might have common information. And so they use some things like 1 to 1, where each table only goes to one other table, or there's 1 to many, or one table can go to many other things. And so there are these relations and these words that we use in math actually show up in computer science, if that's something that you're especially in databases, if you're going down that route. So if you're trying to determine if a relation is 1 to 1 and you're given ordered pairs, I would draw a picture, because I think that's the easiest way to visualize what's going on. So here we've got two more, one on the left which is given as a table, and the one on the right which is a picture. So on the left, when you're given a table, you can think of it as the same. You can kind of put it in a picture form, if you will, or you can use the table to try to draw lines. So like if I just try to connect with the table, 12.5 has matching y values. Let me use a different color there. Matching y value with 3.21. We've got 5.75 going to negative 4.5. 2.34 going to 7.25. Notice that we have a repeat here, 3.21. So if I don't write that repeat, that basically would mean that negative 12.7 also goes to 3.1. So there's two x values that basically have the same y value. So I want to kind of look for repeats either in the x column or the y column. So we have no repeats in x. And we do have a repeat in y. So no repeats in x means that this is a function, basically. But the repeat in y, this tells us that we have one y value that goes to two different x values. That is the 1 to 1 part, so it is not 1 to 1. So this is another way to kind of think of it, is think of, okay, if I have my list of numbers, are there repeats? If so, it depends on which direction. If there's repeats in x, it's not a function. No repeats means it's a function. If there's repeats in y, it's not 1 to 1. If there are no repeats in y, then it is 1 to 1. So that's another way to think about this. The example on the right, we're given this picture here. So every x is going to only one y value. So this one on the right is a function, if we think of it that way. Every x goes to only one y value, which tells us it's a function. However, there's a y value that has multiple x, because there's multiple x's going to the same y. So there is a y that has multiple x values, which means that that is not 1 to 1, just like the one on the left. So I had an example here where I drew them, and this is 1 to 1 because there's basically one connection between every number. But here, in the second example, 25 has 2 connections, and so that's what makes it not 1-to-1, because it has 2 connections on the y side. If there was a number on the x side, I can label these as, say this is x and this is y. If there's 2 connections on the x side, then that would mean it's not a function. And if something's not a function, then it can't be 1-to-1, because in order to be 1-to-1, you need to be both a function and 1-to-1, basically. So anything that's not a function, you just automatically can't be the other thing. I'm just making note of that. So anything that is not a function can't be 1-to-1. Oops. So that's an easy, if you're trying to determine if something is 1-to-1, first check if it's a function, because if it's not, then there's no point going further. It just is not going to be. So there's also a way to do this graphically, other than just looking at sets of ordered pairs. And this is going back to the criteria of 1-to-1, is that it first needs to be a function. And graphically, that means it has to pass the vertical line test. So that means that you can draw a vertical line anywhere, and you're only going through the graph once. The second qualification, that if the y values match, then the x values match, we call this the horizontal line test. So it's just like the vertical line test, except that it's now horizontal. If you draw a horizontal line, it only goes through the graph once. So what makes something 1-to-1 is that it follows both the vertical and the horizontal line test. If it meets both of those, then it's 1-to-1. So I've got 2 graphs here. One is just a set of ordered pairs, and then one is actually a continuous graph. I shouldn't say it's continuous, but it's not ordered pairs. So on the left, first we need to determine, is it a function? So that's the first step. First we need to say, is this a function? And then we check for the 1-to-1. And that's for both of these, so I'll just write this down. So a function means if I draw a vertical line, I only hit one part of the graph. So in this case, I'm only hitting one blue circle anywhere I draw a vertical line. And so all of my vertical lines, I only go through a single blue dot. So this is a function. So then we want to look at 1-to-1, and that's the horizontal line test. So you're going to draw a horizontal line through each of these points and make sure you only hit 1 point. And then this is where not a very good horizontal line. This is where we run into a problem, and I'm going to highlight it right here, because that horizontal line hit 3 different ordered pairs, 3 different points. The horizontal line test, you can only hit 1. So because of that, it is not 1-to-1. So it's a function, but is not 1-to-1, so it is not a 1-to-1 function, because it has to be both. So not a 1-to-1 function. It violated that horizontal line test. So now let's look at the one on the right. So first, is it a function? So I'm not going to draw every single possible line here, but you just kind of want to eyeball. If I draw a vertical line anywhere, am I going to hit the graph only once? Now, even though these look like they're straight, you're really only hitting the graph once here. So this is a rational function, which was covered basically at the end of week 6 and then like the start of week 7. So the beginning of this, you kind of talk a little bit more about rational functions. is it at the end of there's some definitely you've covered it week 7. It might be because next we do so it's got to be at the very beginning of this week in the first couple sections. But so even though those look like I'm going to hit the graph only once, or more than once, I really don't. So these are functions. And so then we look at the vertical or the horizontal line test and the same thing. And so clearly if I draw a vertical line there, I'm only going through the graph once. And here, even though it looks like I might be hitting the graph more than once, I'm not. I'm only hitting the graph once. And so even though these look like they might be getting straight, they're not. So no matter where I draw my horizontal line, I'm only hitting the graph once. So this is also 1-to-1. So it's a function, it's 1-to-1. So this is a 1-to-1 function. So that's how you can determine it graphically. So we've looked at it with ordered pairs. Now, the first one was like, what happens if I graph those ordered pairs? And then you look at it. And then if you have an actual equation, and you graph an equation. So the next part is what happens when you're given an equation and it's not graphed. So this is what we consider algebraically. So if you're given an equation, not a graph, you use this method basically. And so this is the set of procedures is you basically take, well, first you need to determine if it's a function. And so we do that with the vertical line test, or in this case, we have to just know, basically, is this a function? If it's in function notation, then yes. If it's in function notation, automatically that part is good. So then we need to really check the 1-to-1 part. So we go back, I'm going to go back to the definition of 1-to-1. So the first definition here, A equals B, A is not equal to B, then F of A is not equal F of B. As I said at the beginning, that's sort of hard to understand, and it's really hard to prove. So that's why we go the contrapositive. So, and that's what we do for the horizontal line test for all of these. So that's the same thing we're going to do when we do this algebraically. We're going to start with our assumption that the y values are equal, and then we're going to start doing some algebra to get to the point where the A and the x values, A equals B, those are equal. So you're going to start with one assumption and then do math to get to the end. And if it's impossible to get to A equals B, then it's not 1-to-1. So this is a type of mathematical proof. It's very different from proofs you may have done in geometry. But mathematical proofs, you usually assume something and then you do a bunch of algebra to see if you can get to your endpoint. If you can't, then you can't prove it. So we assume that the function values are equal at any point A or B. The key here is we never use numbers for A and B. So you never want to do this by just picking a number for A and a number for B and then doing the math. And that's because you may prove it for one point. You need to prove it for all values. Because in order for something to be 1-to-1, it has to be true for all values. And so that's why we use A or B. We don't actually plug in numbers because that only proves a specific case. It doesn't prove everything. And it's sort of the same thing with finding an inverse, is you have to do it with the actual function. You can't just plug numbers in. Even or odd. When we were learning about even and odd functions and symmetry of functions, x-axis symmetry, y-axis symmetry, you don't want to do those by plugging in numbers because that's just looking at specific numbers. It's not looking at the whole function. We always like to do these with variables. So we're going to assume that f of A equals f of B, and we solve for A. You can solve for B. You just pick, you have to solve for one of those variables, and then you look to see if you get A equals B. If you don't, it's not 1-to-1. So it's really not that bad. It's just an exercise in following the rules of algebra. So I have two examples here. These are both functions because they're given in function notation. The first one is linear. The second one is quadratic. Those are all part of the parent functions that we learned about. So recognizing the parent functions helps you recognize these are functions, so I don't need to check that first step. These are already in function notation. But I'm going to just write that down. If you're given a y equals, you do need to check that it's a function. But these are in function notation, so we know that these are functions. So we're going to assume f of a equals f of b. And so in this case, f is going to be h for our first example here, because that's the name of the function. So we're going to assume h of a is equal to h of b. Then, instead of writing h of a, I'm going to write what h is equal to, but with a as the variable. So that's going to be negative 3a plus 2. And then on the right, it's going to be negative 3b plus 2. So I set my assumption that the y values are equal, and then I actually plug in those x values. So now I'm going to solve for a. So first step, subtract 2 from both sides. So that gives me negative 3a equals negative 3b. And then we divide both sides by negative 3. And we get a is equal to b. So we started with h of a equals h of b, and we ended up with a equals b once we solved. Because that happened, this means it's 1-to-1. If you start with your assumption and you get to your result, and it's what you wanted, then you just proved it. So we just proved that this is 1-to-1. I was able to solve and get that a was equal to b. So now let me do that with the second example here. In this case, we have the letter m, so I'm going to assume that m of a is equal to m of b, just because the name of the function is m. So everywhere I see x, I'm going to replace it with a and b. So I have a squared minus 4 is equal to b, not b, a, b squared minus 4. And so now you're going to solve. So I'm going to solve for a, so I need to first add 4 to both sides. And I got a squared equals b squared. I'm solving for a, and what I need to do so by taking the square root. So I'm going to take the square root of both sides. Now when you take the square root and you're solving, you always get a plus or minus. So we're going to get a plus or minus, square root of b squared is b. So we get plus or minus b. What this tells us that a equals b, and a is equal to negative b. Because we also got that a equals negative b, this means it is not 1-to-1, because this x value, for this y value, there are two different x values, b and negative b. In order for it to be 1-to-1, there needs to be only one x value, but I got two answers here. So because I got two, a positive and a negative, this means it is not 1-to-1. And you can verify that by graphing these and looking to see whether they pass the horizontal line test or the vertical line test, or both of them. So I'm actually going to open up Desmos. So once it loads, I'll put in the first function. So you can see the horizontal line test, no matter where I put a vertical, or I keep saying the opposite of what I mean. The vertical line test, anywhere I put a vertical line, it only goes through once. And then the horizontal line test, no matter where I draw a horizontal line, it only goes through once. So it's a function and it's one-to-one, which verifies what we found algebraically by solving. Let me put in the other one. M of x equals x squared minus 4. So here, this is a function. No matter where I draw a vertical line, I'm only going to hit the graph once. But the horizontal line test fails. You can see, if I picked this value right here, it only hits it once. But any other point that I pick, I'm going to hit the graph twice if I draw a horizontal line. So it fails the horizontal line test because there's multiple y values, or multiple x values for the same y. And so that means it's not one-to-one, and that's how we got this a equals plus or minus b, because there's two different values that give the same y. So you can verify your work algebraically by looking at the graph. But you don't want to always do graphing to find the solution, because sometimes you have some really complicated graphs. It might be easier to do it algebraically, but it's a good check. So that is basically what one-to-one is in a nutshell, what it means and how you can determine if something is one-to-one, basically 3 different ways. By looking at ordered pairs, by graphing, and then by actually using the formula and using the actual definition to do it algebraically. So, do you have any questions on any of that? Feel free to unmute yourself at this point if you have questions.